Good afternoon, everyone. It's an honor to be here. Every star in the sky is a sun, and if our sun has planets, it makes sense that other stars have planets also, and they do. And astronomers have found thousands of planets orbiting stars other than the sun. We call these exoplanets. And to introduce the topic to you, I'm going to show you a little clip from this software that you can all download later. It's called Eyes on Exoplanets. And it starts out with this image of what we think our Milky Way galaxy looks like. But the software actually quickly can zoom in to what is actually a map of the stars. Every white dot is a star, and every highlighted star is a star with known exoplanets. In the software, actually, you can zoom to Earth. It'll actually slowly move us in towards Earth. And if we choose, actually, well, here it shows even spacecraft orbiting the sun, which is cool. If we go to Earth, and imagine we're on the west coast of North America, looking at the spring night sky, and we had binoculars, we could see all these stars. So everywhere we look, there are stars with planets. There's a very special patch of the sky where the Kepler Space Telescope stared for 4 years. So if you can imagine, our sky is literally teeming with exoplanets. In the software, you can choose, if you know planets by name, choose one. Here we're going to look at Kepler 186. And this is a special star, and the software, by the way, will zoom into that part of the sky, and you can look at the star and schematically see what the planets are that are known there. There are 5 planets around this star. And why this one was in the news for a while is because one of the planets, Kepler 186f, is in the so-called habitable zone. A distance from the star where a thin atmosphere is heated by the stars, not too hot, not too cold, but just right for life. And here the software zooms in further, and this is where you have to read the fine print. Hypothetical visualization of planet. We're not expecting to get that kind of detail of an exoplanet pretty much any time in our lifetime. But there's the introduction. And just to summarize it in a bit more of a scientific way, this is a common plot for exoplanets showing you the planet size. So Earth size is in Earth radii, Neptune size, Jupiter size, and orbital period in days, ranging from 1 day to thousands of days. This is a log-log plot, so you can just see every point is an exoplanet. That exoplanets are just everywhere, and they come in all masses, orbits, and sizes. And we actually I have this phrase I love in exoplanets, that anything is possible within the laws of physics and chemistry. And what you can see here, though, is that there's planets of all kinds, planets with less than 1 day orbital period. They're Jupiter-sized planets where an Earth should be. And if you look really closely at the densest part of this graph, and it's actually borne out by more complete statistical studies, that the most common type of planet we know of so far is a planet 2 to 3 times the size of Earth, for which actually there's no solar system counterpart, and we don't really understand how those planets form. It's fair to say here that the dark part of the diagram is dark because our technology can't reach there yet. So, out of most of these planets that have been discovered, and the ones that are most useful for us who want to study their atmospheres and learn more about them, are the transiting planets. You can see that little dot going in front of the sun, a star. We don't resolve any stars like that other than our sun, of course, but that's an Earth-sized planet. And you can see that little drop in brightness as the planet goes in front of the star, and as it finishes transiting the star, it returns to normal. That's what we see in astronomy, a little tiny drop, characteristic of the planet's the duration and the shape of the transit. There's a lot of information in there. And initially, when we found planets like this, it could take it can take right now, actually today, tens or hundreds or initially thousands of hours to verify each planet when we see this little tiny light curve to rule out false positives or instrument systematics or other things. Now, in the picture on your left, you can see it's an artist's conception, and this one shows you the atmosphere of the planet glowing. And the main way we study atmospheres today is for these special planets that go in front of their star, as seen from the telescope, the starlight shines through the atmosphere. And just like shining a flashlight through a fog, if you know the original light, that's the starlight or the flashlight, and you know what's missing when you observe it, you can actually pick up what's in the atmosphere of an exoplanet. And this actually is done just to remind those who aren't in astronomy, or other fields that use spectroscopy, we're relying on the fact that gases absorb at very specific wavelengths. It's based on quantum mechanics, but it depends on the type of molecule, actually. And this particular plot is just showing you a cartoon diagram of different molecules, like water vapor and carbon dioxide, and it's showing you how much they absorb as a function of wavelength, visible wavelengths, infrared wavelengths. And so it's just the point is that we have different types of gases we can identify by spectroscopy. So here I just wanted to show you some real data. And for exoplanets, this is among our best data. And what you're seeing here is you're seeing a wavelength in microns. So this is the near infrared. It's a small slice going from 1.1 to 1.7 microns. And on this axis, you're seeing absorption in percent. It's just a tiny, tiny, tiny amount of light is being absorbed by the planet atmosphere. And there's one more little clue you need here. And I want you to think of a planet with a transparent wavelength where nothing's being absorbed. That planet is smaller, appears smaller and blocks out less light than a planet that has a lot of absorption in its atmosphere, will block out more light. So effectively, what we're looking at is a planet changing in size as a function of wavelength. And so if this planet didn't have anything features to show us in its atmosphere, all you would do is see a straight line here. So for now, you just have to agree that these are different from a straight line. And what you see here are you see each panel is a different exoplanet. The blue points are points from the Hubble Space Telescope. That's our best instrument right now to observe planets this way. And the red line and the green points are models that are trying to extract what's here. We do more complicated things than just showing that. So right now, this is our best way to find exoplanet atmospheres through the transit technique. I'm proud to tell you that I invented this technique. I was the first one to write this down. Back in the days, even before we had planets that transited their host stars, I was working on this problem. And now it's like a mainstay in the field. But back when and like some of the other speakers today, timing is everything. And when I was a graduate student in the mid-1990s, exoplanets were first discovered, and I worked on them for my thesis and subsequently as a postdoc. And it's just such amazing to be here talking to you today, because at the time, even people on my own thesis committee or my peers would say, well, why are you working on this? Even people, my senior, would say, well, we're never going to be able to study their atmospheres. They said, well, why are you thinking about high temperature condensates that will form clouds here, et cetera, et cetera. But because nobody was working on it, I was able to work on many different areas in exoplanet atmospheres and characterization, and literally make some of the cornerstones of the field today. And so now today, the field is full of people. We also have a signal to noise problem, but it's not quite as bad as we heard from the last speaker. And so I'm actually leaving this kind of now it's mainstream atmosphere work in the hands of my own former students and some of my colleagues, and I'm moving towards the future. Because in exoplanets, actually the best planets are always in the future. And so while today we can study giant planets and hot planets, we can study things about their atmospheres and try to understand their interiors and orbits, actually it's the planets that I'm most interested in are the ones that could be potentially habitable. And this is just an artist's conception just to convey that we don't know what's going to be out there. We draw upon many fields in earth science, high pressure geophysics, chemistry, biology, microbiology. We're trying to guess what's there, because what we want to do is find habitable planets and look for signs of life in their atmosphere. So I'm now going to just tell you some of the more recent thinking on habitable planets and just how diverse planets are out there. We have this concept I already introduced called the habitable zone, and this is just a graphic showing you radius of orbit relative to Earth's. So Earth is here, and these are our solar system planets. On this axis, I'm showing you different types of stars. So we have our star, the sun shown in yellow, and our Earth, just conveniently, we call it 1 astronomical unit from our sun. It's in our habitable zone. And this blue curve here, all of these, although it's an illustration, it's based on real calculations. So our Earth is in this light blue region we call the habitable zone. And as we move towards smaller stars, that habitable zone gets closer to the star because they have less energy output. And actually, this little blue area is for a planet like Earth with a nitrogen, carbon dioxide, water vapor atmosphere. But it's so hard in our field to think about what else could be out there. And so part of the fun of this job is just imagining all the possibilities based on physics and chemistry. So we've conceived that we could imagine planets much closer to the star, let's say at 0.5 astronomical units, that just have less water vapor in their atmosphere, a smaller water inventory than Earth does, because water is our most powerful greenhouse gas. Less absorption, and there's less chance the whole planet could heat up and lose its ocean. That's a bit controversial for reasons I'm not going to get into now, but a more interesting type of planet are ones that would be out here in this outer habitable zone. These are planets that we think, planets that are massive and cold enough, can maintain hydrogen in their atmosphere. We have almost no hydrogen in our atmosphere. Just like the helium balloon that kids let go of by mistake, the hydrogen will escape to, float away and escape to space. Our Earth can't hold on to it. But there are planets we think are out there with hydrogen atmospheres. Now, hydrogen is a very potent greenhouse gas because actually it doesn't absorb in discrete wavelengths, like the cartoon I showed you before. It's a homonuclear molecule, but it can have collision-induced absorption. If the pressures in the atmosphere are high enough, it can actually have absorption just induced, and that makes it absorb over many, many wavelengths, which help it to be a powerful greenhouse gas. Also, unlike carbon dioxide, it doesn't freeze out, but it actually can stay in gas form to very, very low temperatures. So we're imagining that a habitable world is not just one like Earth, but there's a whole range of possibilities, mostly depending on what's in the atmosphere and what's acting like a greenhouse gas. So these hydrogen-rich atmospheres actually may be our first chance of finding signs of life on another world. And it sounds a little strange. It's like the person looking for her lost keys under the streetlight. But hydrogen atmospheres are very favorable for transiting exoplanets. And the reason has to do with the pressure scale height. Here on Earth, we have a scale height of about 8 kilometers. It's the E-folding factor for the pressure change. Just like when people hike up Mount Everest, they run out of air. But if our atmosphere here on Earth was dominated by hydrogen, people wouldn't run out of air hiking up Mount Everest because their E-folding factor would be much bigger, actually. And it depends on if we could work out the just equations of hydrostatic equilibrium and the ideal gas law, we would derive this equation. Pressure changes with height related to this exponential, and that's what we call the scale height. The term you can look at is this mean molecular mass. On Earth, it's because of nitrogen. If we were dominated by hydrogen, our mean molecular mass would be much smaller, giving us a bigger scale height. So one thing that my team did recently was we looked at, well, the question of whether or not there is life in a hydrogen-rich atmosphere is a separate question. But assuming that life was there, we worked on a detailed photochemistry model and showed that the gases could accumulate in the atmosphere. And those are what we call biosignature gases, gases produced by life that could accumulate in an atmosphere and eventually be detected from far away. So we're here dreaming about exotic planets. We're using detailed models of physics and chemistry and thinking about what we could observe in the future. And on this plot, it's just a theoretical simulated spectra taking into account some types of molecules produced by life that could survive in a hydrogen-rich atmosphere. Okay, so this question of the search for life is where my main research focus is right now. And actually, it turns out to be more complicated than we ever imagined because of this anticipated diversity of planets. So we do make models using basic applied physics and chemistry, but the complication is in the surface sources and sinks. There's lots of gases produced by life on Earth that we hope to see on planets far away, but what we're trying to do now is figure out amongst all the false positive scenarios, how can we really evaluate each case? And in the future, when we find gases that don't belong in the atmosphere, we're in atmospheres that's very out of equilibrium, gases that may be produced by life, we have a lot of work ahead of us to be able to figure out all the details and to know which ones may or may not be produced by false positives. So I did want to finish off with a few slides about our future. And that is how we're going to observe exoplanet atmospheres and look for signs of life on them. Well, I'm excited to tell you our first chance is coming right up. We have a NASA-led, MIT-led NASA mission called TESS. There's a little picture, artist conception of it in the far right. And that's actually, we're building that right now at MIT. A lot's going on here. We're going to search the entire sky looking for planets that transit their stars that are relatively close by to Earth, tens or hundreds of light years away, so that we can look at their atmospheres with our next generation Hubble. We call that the James Webb Space Telescope. This telescope actually is effectively 6.5 meters in diameter. This sun shield is tennis court size. And if after this you Google James Webb Space Telescope, you'll actually see real photographs of these gold-coated mirrors out at Goddard Space Flight Center that right now the covers are off the mirrors just temporarily actually, so people can take photos through the window and see how great it looks. But we have a big future ahead of us here, and it doesn't stop with these telescopes. A lot of the work that I do now and others is conceiving of and working on technology to make even more powerful telescopes happen in the future so that we can survey stars for the smallest planets. Now, until that time, that we can find the small planets and characterize them and see which ones are habitable, which ones may have life on them, I'll just leave you with a few Exoplanet Travel Bureau posters. This one is Kepler 186f. That's the planet I showed you at the beginning with that software. Kepler 186f, where the grass is always redder on the other side. This planet this orbits a small red dwarf star, and people just speculate about different pigments on any hypothetical vegetation. experience the gravity of HG 40307G, a super-Earth. This is a planet whose surface gravity is about 1.5 times that of Earth, and they're just imagining a future tourist traveling there and skydiving. Relax on Kepler 16b, the land of two suns, where your shadow always has company. And this is a planet that orbits two suns, actually, circumbinary planet. And I just have to say, in exoplanets, we are definitely a field where fantasy is big right now, but so far, exoplanets has always delivered. And so I just want to finish by telling you that the next time you go out and look up in the night sky on a clear night, you can actually wonder which one of those stars has a planet like Earth, because we know that the small rocky planets are out there just waiting to be found. Thank you.
If you have questions, go to the microphone. There should be this.
Very loud voice. Could you comment on the potential for seeing oxygen atmosphere?
Yes, can I comment on the potential for oxygen atmospheres? Okay, so oxygen is something that, believe it or not, this famous astronomer Jeans in the past, in 1930s, first wrote about the possibility of oxygen as being a sign of life on another planet. It is, in some ways, our most robust biosignature gas, because on Earth, without plants and photosynthetic bacteria, we would basically have no oxygen. However, in the last couple of years, astronomers have concocted several different scenarios of false positives. I'll just run one of them by you. It's my favorite one. And that is of a planet very close to a small star. These small stars, before they get on our main sequence and burn hydrogen stably, before they essentially become a star, they have a very long period of very high luminosity. So a planet in the habitable zone of a small star, it had a lot of time that it was blasted by heat and radiation. And people think that that type of planet may have lost not only its ocean, but water in its mantle, and that water just kept coming up, and we get these desiccated planets with a massive oxygen atmosphere. So out of all these kind of somewhat concocted false positive scenario, that would be my talk about a year from now, is which observational markers with spectra can we help rule out those false positive scenarios. So to summarize that kind of long answer, yes, we're still excited about it, but it's not as promising or robust as it was in the past.
Other questions? Nobody? Please step up to the microphone. There's a fear of microphones here.
You get many planets likely around brown. Oh, I've got to switch it on. Are there any planets around brown? That doesn't seem to make any difference either. Around brown dwarfs, and if so, how common would they be? And in
Yes.
particular, also how likely it is they would be habitable and detectable.
Okay. Yes. Well, I'm only hesitating because of some embargoed news that I can't talk about. It's not my work, someone else's. But I just want to say that astronomers are looking around every possible star type that is out there. And the smaller stars right now easier to find planets around. So what the question was about are very small stars that are essentially faint stars. People are looking around dwarfs. They haven't found planets around them yet. But right now, people are going down smaller and smaller and smaller stars actually. So we don't have an answer for that yet. And we will as the years go by. We expect them to be there, but we haven't found any yet.
If there are no more questions, thank you so much.